In this module, we'll demystify how TPUs actually work. You'll see what a systolic array is, how TPU cores and memory are organized, and how XLA compiles your model. By the end, your GPU intuition will carry over cleanly to TPUs. Traditional CPUs, and even many GPUs, are generalists. They're like a Swiss Army knife, flexible, good at branches, conditionals, and a wide variety of tasks, but each individual operation isn't maximally efficient. Deep learning is different. It's dominated by massive matrix multiplications with very predictable patterns. TPUs are specialists for this world. They give up some general flexibility and complex control flow, so the hardware can be tightly tuned around dense tensor operations and steady high throughput. A systolic array is essentially a grid of tiny Mach units that pulse like a heartbeat. Inputs stream across the array, while weights stay loaded in place. Each cell performs a multiply-accumulate, then passes partial sums down to its neighbor. Because data flows locally instead of returning to external memory, reuse is extremely high, and bandwidth needs stay low. This pattern is ideal for deep learning matrix multiplies, where the same weights are applied to many different inputs. A TPU core is built around three main ideas that map directly to neural network workloads. First, matrix units do the heavy lifting for GEMs and convolutions, dedicated hardware engines for multiplying large tensors as fast as possible. Second, vector and scalar units handle the glue work, activations, element-wise operations, and control logic around those matrix multiplies. Finally, a unified on-chip buffer feeds these units with high bandwidth data, cutting trips to slower external memory and keeping the systolic array busy. You can picture the compute core as a planet and each memory level as an orbit around it. Closest in are registers, tiny but incredibly fast. A bit farther out is on-chip buffer or shared memory, still fast with more space. Farthest away is HBM or external memory, huge but slowest to reach. Every accelerator follows this basic pattern. Your main performance goal is simple. Keep hot data in the inner orbits and touch the outer orbits as rarely and as efficiently as you can. TPUs scale by repeating a simple building block. At the lowest level are Mach units, tiny multiply, accumulate engines. Many Machs arranged in a systolic array behave like one massive matrix multiplier. Several of these arrays live on a multi-core TPU chip, sharing high bandwidth on chip memory. Then chips are wired together into a pod using a toroidal mesh network. Those dedicated links let you run synchronous data parallel and model parallel training across hundreds or even thousands of cores. XLA is the translator between your high-level code and TPU hardware. Instead of executing every TensorFlow or JAX operation one by one, XLA captures the whole computation graph and compiles it ahead of time. During compilation, it can fuse operators, plan memory, and choose data layouts that match the TPU. What you get is a single, highly optimized TPU program that runs much faster and more efficiently. On TPUs, execution is based on a static graph planned ahead of time. You pay an upfront compilation cost, but once the graph is fixed, the hardware just streams data through it with almost no decisions at runtime. That's how you reach maximum throughput. Dynamic execution on GPUs works the other way. Each step can react to data, change shapes, and take different branches. You gain flexibility and easier debugging, but you introduce runtime overhead and usually give up some peak efficiency. To get good performance on TPUs, both JAX and TensorFlow try to feed XLA clean, self-contained chunks of math. In JAX, decorators like JIT or PMAP take a pure Python function, capture its array operations, and hand that computation graph to XLA. In TensorFlow, F-function and TPU strategies play the same role. They trace your code into a static computational graph. The common goal is to isolate side effect-free tensor computations, so XLA can aggressively optimize and map them onto TPU cores. Dynamic shapes are one of the biggest performance killers on TPUs and, to a lesser extent, GPUs and Ascent NPUs. Whenever your sequence length or image size changes, the compiler may need to generate a new program variant. That costs both time and memory. Padding and bucketing are the standard fix. You group examples into a few common lengths, then pad everything inside each bucket to that fixed size. Now the compiler optimizes just a handful of shapes and you get a fast, reusable execution pipeline. NVIDIA GPUs and Google TPUs execute your model in very different ways. On GPUs, the hardware schedules individual instructions dynamically. Kernels are often compiled just in time. So eager, Pythonic code with branches and changing tensor shapes usually just works, even if it isn't perfectly efficient. TPUs prefer a pre-planned route. XLA compiles the whole graph ahead of time into a static data flow program. You get excellent throughput, but mainly when shapes are mostly fixed and loops are neatly fused. For TPUs and many NPUs, performance is largely about how you structure the computation. They thrive on big regular blocks of math, static shapes, pure functions, vectorized tensor operations, and large batches that run the same way every step. What hurts is code that keeps changing shapes branches heavily with Python ifs and fors inside the training step, or constantly moves data between host and device. So think in terms of compile-friendly, array-style code instead of dynamic, step-by-step scripting. TPUs work so well because the entire stack is designed as a single blueprint. At the hardware level, systolic arrays are the engine. They drive dense matrix math through a fixed, rhythmic data flow. To feed that engine efficiently, XLA expects a clear contract from your code, mostly static, predictable graphs that can be heavily optimized ahead of time. When your model respects those constraints, the payoff is huge. Tightly synchronized chips, high utilization, and cluster-scale AI that feels almost like training on one giant accelerator.